Hello all, and welcome to the Culinary Chemistry Lab cooking show. My name is Chef Aidan, and today I'll have a guest with me who will be assisting me in cooking and learning about transport phenomena involved in it.
Ooh, what will we be making?
Well, today we'll be making chicken parm because it uses every aspect of heat transfer.
What is that?
Well, heat transfer occurs whenever you have a high temperature and a low temperature surface. The high temperature will transfer that heat from the high temperature surface to the low temperature surface through three different types: conduction, convection, and radiation. First, we'll start with conduction. Conduction involves two different materials that are directly touching and at different temperature points.
Oh, like the chicken touching the pan?
Yeah, so we've coated the pan in oil because oil has a very high thermal conductivity in comparison to the pan itself. This will also allow direct contact on the bottom of the pan as opposed to just a flat pan surface.
What the heck is thermal conductivity?
Well, for that, we'll cut to our resident chemical engineer.
Thermal conductivity is a measure of how well a material conducts heat. The oil conducts heat to the chicken much better than the air. We denote thermal conductivity with a K, and we use it in many of our equations. One of these equations is known as Fourier's law. This equation relates the temperature gradient and the thermal conductivity to something called heat flux, which is the rate of heat transfer per unit area. Fourier's law is used in the heat equation, a general equation that can be applied to all types of heat transfer and is used in many different heat transfer problems. In our scenario, many of the terms can cancel out. We can assume heat is coming only from the source beneath the pan, so the heat generation term goes to zero. Because the heat is directly below the pan, heat transfer is occurring only in one direction, so the y and z terms also go to zero. This leaves us with a simpler form of the heat equation. In steady-state circumstances, the accumulation term will also go to zero, as nothing is changing over time. This leaves a simplified form of the heat equation that is equal to zero and is equal to the derivative of the heat flux with respect to x. As the derivative of the heat flux is equal to zero, the heat flux is constant in these circumstances.
Oh, neat!
Yeah, so now we'll move on to our next mode of heat transfer, convection.
Oh, there's a button on my oven that says that.
Yeah, so convection is whenever heat is being pushed around with a fluid over an object. So in your oven case, that's whenever the oven pushes air through the oven at a high temperature to cook the things inside of it. So the air in your oven will be moving as part of forced convection, where it will blow from one side to the other. But there's also free convection, and that happens whenever air densities are different, or even fluid densities, like whenever you're boiling water.
Forced convection occurs when an external force, in this case a fan, moves a fluid, in this case air, across the surface of an object. The constitutive equation for convective heat transfer can be seen here, where Ts is the temperature of the surface of the object, T infinity is the temperature of the bulk of the fluid, and H is the convective heat transfer coefficient. This value comes from velocity and the physical properties of the fluid.
So there's four different regimes of boiling. The one we'll be looking at is nuclear, which is the one that uses the energy most efficiently when boiling water.
Nuclear?
No, not nuclear. Nuclear. Our resident chemical engineer will tell us a little more about it.
The ideal temperature for boiling is 5 to 30 degrees Celsius above the saturation temperature of the fluid. This difference is known as the excess temperature. When the excess temperature is 5 to 30 degrees Celsius, we call it the nuclear boiling regime. This regime is the most efficient for heat transfer, as the hot surface is mostly in contact with liquid water, which has a higher thermal conductivity than water vapor. In this regime, we see individual vapor bubbles form, and then form what we call jets and columns.
Is it time to take the garlic bread out of the oven?
Yeah, go ahead. Wait, stop! You need oven mitts.
What will oven mitts do?
Oven mitts add an extra layer of thermal resistance, so you don't burn your hands on the hot pan.
What is thermal resistance?
Thermal resistance is a way of measuring how much a material will resist the transfer of heat. It is the ratio of the temperature difference between two surfaces for conduction or between a surface and a fluid for convection to the heat transfer rate. For a composite material, an object made up of several layers of different materials, the total thermal resistance is equal to the sum of the thermal resistances of each layer as well as any thermal resistance at the fluid boundary.
Thanks for tuning in this week. Next week, we'll be interviewing Iron Chef Barry Sotfot. Make sure to tune in